Okay, so talking about passion, I just, Yuval was in UCLA when my NSF proposal was rejected for its too theoretical. So I spent, or useless or whatever, so I spent my life on useless theoretical stuff. When you do this, to prevent cognitive dissonance, you have to insist that you are doing something fundamental and all this and all this. So I'll try to convince you about this. So first, the title. I don't, is I different than 12? But it's 1 different from 12. So this is not English. I don't know where this from come from, but this is what it is. And what is this topic? It's essentially the mantra that drove my thinking over the last 2 decades. But so this talk will be about why this question is so important, but it also will be that in some way, you know, when you do transactional memory, I would say that you are doing engineering. It's something to be used, and there are trade-offs, and you have to make some decisions which are not, cannot be said this is completely right and this is completely wrong. In mathematics, there is completely right and there is no. I used to ask my kids when they were young a question in math, and they will come, and the answer is 93. They will tell me, but the answer was 94. They will say, but it's close. I had to explain to them the notion that there is no difference between when the answer is 94. If you say 200 or you say 93, it's the same. It's the same Hamming distance. So. I'll try to convince you that I think that I was doing mathematics, and in mathematics they say that God gave the numbers and the rest was created by man. And my saying is God gave us read-write, and the rest we created. But read-write is so special; it was created by God. Must be. Okay, and essentially, what I'll give, you know, I'm not going into Hilbert spaces to convince you about this, and I will actually, the thinking of the distributed computing is as in some way elementary as mathematics. You know, you build things, but the beginning, you don't have to start there. The beginning of mathematics is few axioms and distributed computing. It's the same, unless you put all sorts of stuff that doesn't need to be there. Okay? And I'll then convince you that this is, in this talk we will see a lot of back and forth in presentations of algorithms in distributed computing, either through geometry or through code. And you can, this is a complete duality that can be interchangeable. And the question is, if there is a duality, what should you use, geometry or code? And we'll see in some situations, the geometry gives you a lot of insight. In some situations, it becomes, the algorithmic stuff is so simple that when you try to imagine how it looked geometrically, it is hairy. So I'll try to give you examples. So all this I promise in the span of an hour. Okay, so what is this 1 to 12? We have the task of consensus, and we can view it in two ways. The task of consensus, either all processors start with input 0 and 1, and they do some negotiations, and at the end, they all stop, all of them 0 or all of them 1. To prevent trivialities, we say that if everybody starts with a 0, they have to end up with a 0. They cannot end up with 1, and vice versa. But there is also a version of it which is election. They elect a leader. So everybody submits their ID, and one leader is elected. And here, to prevent trivialities, you say that only a processor that took a step in the algorithm, and this is the notion of participating processor, only a processor that took any step indicated, I want to be a leader. So you don't elect somebody who doesn't want to be a leader. Only it can be elected. Okay, so this is the consensus. This is 1. In 1990, Somachadure came up with an ingenious variation of consensus, which is even if we say that the first POTSI was in 82, this is 1990, 8 years later, you wonder why it took even 8 years to get to this question. And this question is supposed to be a generalization of consensus. And it also, like consensus, it also can be presented in 2 variations. One is that corresponds to the 0-1 variation, which is now instead of giving 0 and 1, which is we have to choose 1 value out of 2 values, now we'll view the problem as choosing k values out of k plus 1 values. So we have processor wake up with k plus 1 values, and they have to negotiate and output, each one of them output a value from here. And together, the number of values, the set of values they output shouldn't be bigger than k. So one value that may be an input should be excluded, again, to prevent trivialities. If when processor submits an input, if there is an input that was not submitted, it's not allowed to be output by anybody. So you cannot just have default values. And I see some faces. Maurice, feel free to stop me and interrupt me and attack me viciously, because I pride myself that I take as much as I give. So then there is the version that corresponds to election. Processor put IDs. And what they need is each processor will output an ID. We have now n IDs. And what they output is at most, each processor, when I look at the set of output, together it at most k IDs. Okay, so we have, in analog to the consensus, we have here 2 versions of the k set consensus. So we have, to me, what was the question, is this the only analog between k-set consensus and consensus? Isn't it the case that anything that I can say about consensus should have the generalization to k-set consensus? There may be an argument, one may come with one generalization, one will come with another generalization. I don't know how to say that this is the right or wrong generalization, but there has to be a generalization. There should be nothing that happens with 1 that doesn't happen with k, because why should distributed computing distinguish between 1 and k? You know, if you come to me with numbers, say 1 is special. If you take a number and multiply it by 1, you get the same number. But in distributed computing, what makes 1, what should make 1 so special? So my, if you want, meta thesis was everything should be generalizable, and let's see how far, whether I fail at some point. So with this idea in mind, I came to many people and say, let's investigate this, and so this I'm going to report work which among the transparency was too small even to put them in. We have Yuda here, and Rashid, and Michel Ragnal, and Corentin, And who else? I think it's what? Sergio. Sergio, of course. Sergio, oh boy. Don't tell him ever that I, okay, Sergio. Okay, so let's do some examples. With consensus, we have this thing called test and set. What is test and set with set consensus? What's the analog of test and set with set consensus? And it comes out, the test and set come out, you give me two processor consensus, and I make from it what is called test and set for any number of processors. And what is test and set? Any number of processors, each one of them want to be a leader, and one of them says, I'm the leader, but the leader is the wrong word here, because the otherwise say, I'm not the leader, but they don't know who the leader is. So there is a big difference in saying I'm not the leader and knowing who the leader is. Just to say I'm not the leader, two processors consensus is enough. To know who is the leader, you need that all the processors will have consensus. So what is generalization of this? We know that the two versions of consensus that I've shown you, 0-1 consensus and election, are equivalent. With election, I can do 0-1 consensus very easy. Each processor, before it starts to take steps in the box of election, first write what it votes for, 0 or 1. Then you get with a winner. It must be that the winner already wrote what it voting for, and you take his vote, or her vote. In the opposite direction is more interesting. If you give me 0-1 consensus, what processor do? They come in shared memory and or whatever you want other domain. They write their binary expansion, and now you look and you say, I want to vote for myself. My first bit is 1, so I'm voting for 1. But 0-1, okay, 0-1, now you cannot fight for yourself anymore. So you look at all the names that start with 0, and you take one bit. Maybe there is only one bit. You take one bit and you vote for it and continue and build the ID in log n phases. What is it already at this point, if you start to think of it, how you do it with this k set? How from k values you build k election? That's already problematic. Finally, we have Lamport and Schneider, very almost as old names in distributed as Katz, the Shmuel Katz here. I can say old because today I went on the bus of bus number 25 that takes me from the house takes me from North Tel Aviv to the university, and you'll not believe it. I gave the guy $5.80, and he looked at me and say, "Senior or regular?" I'm 60 already, but how old is senior? And he says, 67. I wanted to get out of the bus. This is after I quarreled with Hagit and who is more resembles Clooney and stuff like this. And this guy comes and says 67. I couldn't believe it. So when I say old names like Shmuel Katz, I'm not insulting anybody. And it's not insult because we still remember him. Him and Francis. Okay. Well, I'm old enough to remember him. Okay, so let's forget about, I want to move to the interesting stuff. Test and set, for example, you can see this is an old stuff. What will be test and set? Well, if you give me, what is two processor consensus?
Maybe you repeat what test and set means.
Okay. Test and set is out of any number of processors. One processor will output 0, all the rest will output 1. So one processor will know I'm distinguished. Okay, this is test and set. And test and set I can build out if you give me the construct of any two processors can do a consensus, can solve consensus. From this I can build test and set. Here it is. I take two processors, I do consensus between them. Okay? The winner continues to next consensus where 3, now a new processor went in. And out of this will come, remember that the process that output 0, if you're supposed to output 0 and you die, you output 0. Okay, so it's about completion and stuff like this. So from this sieve will come only one processor that will output 0. And all the rest, at some point of time, they will lose. There is like a competition here. All of them will lose and output 1. Okay, and you see that this I can build now infinite tree for any number of processors. Similarly, I can do the same. What is generalization? The two-process consensus is you take number of processors and you vote for number of processors, one less than the number you have. So this corresponds to I have k plus 1 processors, and I will output only k. Okay? So the generalization will be, I have any number of processors. At most k of them will output 0, and all the rest will output 1. Okay? I can easily build it. Just take any k processors here. At most k plus 1 processors here. At most k will come out. This k will join with another processor. At most k will come out, At most k will come here and output 0. Easy generalization. While we know this is true for testing. This is true for testing. We know that from k plus 1 processor, k set consensus, which I'll repeat it is, I have k plus 1 processors. Each of them wants to get elected, and one of them will not get elected. Out of this, if you give me this construct, you cannot build, we can prove you cannot build k plus 2k election. But when you are talking about the version of test and set, that they just output 0, 1, if you just give me this box of k plus 1k, you can build the 0, 1 for any number. Okay, so.
You assume there are no failures?
Pardon?
You assume no failures?
I always assume, I will never assume no failure. Never. So you see, when I say output, it's a potentially output.
Okay.
It's a potential. If this processor is supposed to output, if it may run here, win everybody, and just die here. But he's the 0. The fact that he died, I don't talk about posting the 0. This is another matter completely. Okay, so what about 3? What about? So much aduri. So we talked about there is generalization, and you cannot argue with a generalization. How can you argue with a generalization? A good generalization pushes you, gets you further than a not so good generalization. So much aduri gave us a generalization of consensus. And in particular, well, we saw that her definition, sort of generalization of binary consensus, will be k plus 1 values, and you narrow them to k values. So you see from 0, 1, you exclude one value. You can view it as excluding one value. From k plus 1 values, you exclude one value. So this is a generalization. But is this the right generalization? Second, we have seen that there is a difficulty here of binary consensus equals election. How do I do it when I have from narrowing k plus 1 value into k? How from this I do the trick of this log n rounds by which I elect a leader. Not only I think that the statement of properties should be generalized, but if you come with an algorithm to do something with consensus, there should be an analogous algorithm, not only the analogous property that you can achieve it. If you achieve it in a different way, there is something wrong here. It's not so. So to show you all this, what is generalization and what is a better generalization, perhaps, so you can push farther, and I will. The epsilon didn't. How did it? I don't know. It floated. The epsilon jumped from here to here. All of distributed computing on one foot, and I gave this talk in Tunis. A week ago or something, and I told the story that everybody knows of Hillel and Shammai. Anybody here doesn't know what the expression on one foot? You'd be ashamed. There are. Okay. So, yeah, I forgot. You see, being in the States, from דברים שרואים משם לא רואים מכאן, or whatever. I hear.
In Tunisia, everybody knew
Pardon?
the story?
Oh, no, I'll tell you why I recall Tunisia. Okay. So the story is in the times that we are talking like 2,000 years ago, when there still was some of our Jewish ancestors in the Holy Land. There were two schools of thoughts. It's like we have today, liberals and conservative. This was 2,000 years ago. There was no secular people. Everybody was religious, right? So the conservatives, the strict interpretation, literal interpretation of the scripts of religion were led by this guy Shammai, and the other was led by this guy Hillel. And the story says that this person came to Shammai and says, teach me the whole scripts while I'm standing on one foot. Shammai kicked him. What a joker. What is this? This is so deep. It takes years to study. But you're joking, you on one foot. You'll stand an hour on one foot. I mean, if I'll torture you, you'll stay 2 hours. But he went to Hillel. And Hillel said, you want to learn it on one? I'll tell you. And this is where Tunis came from, because growing up religious, I know how he said it. And this is Aramaic. And I just learned, I didn't know. I don't know what the argument. There is this friend, Rashid, that few people here know. In some of the arguments, don't you know that Arabic and Hebrew come from the same root of Aramaic? I didn't know that. It's not true. It's Assyrian. There is a root. Why so many words are the same?
No, Hebrew and Arabic are Semitic, but Hebrew and Aramaic are and also Aramaic, but Hebrew and Aramaic are the two close ones. Arabic is further away.
I see.
All Semitic languages, but it's not.
So I thought that if I said in Tunis, I didn't say, so Hillel told him, "Mai desani Allah lechaverach la ta'avid," meaning what is you hate, don't do to your friend. Ve'idach zil gmor, and the rest go and study. This is the whole thing. This is the summary of the whole thing. The rest is just details that you have to. And I thought that, why didn't I try there to say it in Aramaic and see whether something, I completely understand it. I mean, zeal is go, and I don't know. I don't know if it's the right or not. Anyway, so this is everything on one foot. Just the principle from here on. It's really development on this. And to me, distributed computing is this slide. And it never failed. Okay, and I said on the way to, if Maurice did this slide, It will be so colorful, and people will come and will carry weights and stuff. So let me tell you the story behind this lame transparency. This is what I call Epsilon Agreement. What is Epsilon Agreement? We have a group of people sitting in each corner here. It's a group. And they want to output a point in this, not as a group, but each person wants to output a point in this triangle. And what do we want? We want them, all of them, to output points which will be close in a radius which will be circumscribed in a circle of diameter epsilon, where epsilon is your parameter. You give me an epsilon, and I will build an algorithm to solve it. Again, I need to prevent trivialities. They will always output the center. For this, to prevent trivialities, or that's the interest, that's part of the, there is the notion again of participation. A group participates if anybody in the group took a step. So if only this group participate, they have to output this point. If two groups only participated and finished, they cannot wait, remember. They have to output points just restricted on this line. And otherwise, if all of them participate, they can output anywhere. Okay? And here's the algorithm to solve it. And once you know how to solve it, you solve distributed computing. This is also an interesting, this distributed computing, a lot of time we talk about full information and stuff like this, and by full information I mean you know all my history and stuff. This says that actually, perhaps you can say it, I don't think it's encoding. So this is a question. This is here, these algorithms that I said encompasses all distributed computing does not do full information. And probably I claim you cannot recover. I don't say it will be less bits of exchange, but and it's an interesting question. We have many ways to solve it, whether all of them, information theoretically, are the same, or which one is more efficient. So how do you solve it? How do you solve it pictorially easily? You solve it by, this is an algorithm that some of us have been using from the end of the 80s. I read that some of us who didn't know this algorithm as folklore, David Peleg in the community of robotics now has an algorithm called, I think this is it, center of gravity algorithm. So this is a center of gravity algorithm. What is the idea? The idea is that we have in distributed, we have these registers which we call multi-reader, multi-writer. Everybody can write into these registers. So these registers, there is a pile of registers which at the beginning are all initialized to 0. And we interpret putting a 1 here as putting a unit weight on this side. Okay? So if all of them if one of them put a unit weight here, and then somebody else put a unit weight here, it will appear as a single unit. It's not an addition of unit, because it already was written 1. So you write 1 on top of 1, you changed nothing. Okay? So what will be the algorithm? The algorithm is the observation that if you have a system and you put enough weights on the corner together, enough weight, if you will add a unit of weight, you'll change the center of gravity by something proportional, inversely proportional to the weight of the system. Okay? So what we will do is we will start to put weights on the corner, processors will start to put weights on the corner until they will get to a weight in which the addition of 2 units of weights move the center of gravity by less than an epsilon. And then they look at the center of gravity and output the center of gravity. So what is the algorithm? A processor looks at the system, looks at this, how much weight I have here, how much weight here, how much weight here, and will say if the system is below this critical weight W, I go to the next zero that I saw here. It first looked at this. It say, here is a 0. If the system is not weighty, I'm going to go and put a 1 here. So he looks at the weight. System is not weighty, goes to put a 1 here. In the meantime, the system might have moved, I don't know where, and there is a 1 here. Then it didn't change anything. Okay? So you look at the system, you put a weight. You look at the system, you put a weight. Eventually, if you do this enough times, the system at least will be more than W. Okay? The moment that you look and you see the system more than W, stop. Don't add any more weights, nothing. Look at the center of gravity, return it. Okay? Now I claim we solved the problem. Why? Because one of them may stop when the system is exactly the W. Another one may not see that the system is he looked long time ago, and in his side there was no addition. Now he puts another weight, it's W plus 1. But anybody that will observe, in order to put the next position, you have to observe the system. There is no possibility of putting on this side another one. But we have 3 corners, and therefore there is a possibility of another corner. I think there is no possibility of 3, but it doesn't matter. Anyway, the system is weighty enough. It will not, so they at most see W plus 1, or W plus 2, but all these center of gravities are different. And of course, on the same side, people may see different centers. The fact that you're on the same side doesn't mean that you'll see the same center of gravity. Okay? And this solves the problem and satisfy our conditions, because when you are alone, there will be 0 and 0 here, and you'll add, and then you'll stop, and the center of gravity will be here. And if only 2, the center of gravity between these 2 is on the line, and we solve the problem. Okay? Distributed computing on 1 foot. Okay, so why do I say, why read-write, I say is given? Because we can solve this, and due to our distinguished friend here, Maurice, and Nir Shavit that are not, we know that's the only thing we can do. You cannot do more. And you cannot do, this is the only thing, and if somebody said, I want you to solve Epsilon Agreement, but here there is a forbidden area. You cannot do this. So these registers, read and write, corresponds to in nature something very natural, which is a triangle. And if you go to a triangle, you go to higher dimension, it's called subdivided simplex. But in higher dimension, there are things which are completely crazy. And the simple things that we know about, which is like a ball, is subdivided simplex. Read, write corresponds to the simplest thing in geometry in higher dimension. But everything has, so what I can say. If I triangulated this, if I took a triangle and triangulated it, meaning in the plane I put a point and connected and so forth, okay? And then you ask me to, let's say, I want all the points to output from the same, I want all the processors to output from the same triangle. In other words, processor will output, you do not allow that one processor will output from here, this node, they will output nodes in this picture. They are not allowed in the same constraint that we had before. If a group goes alone, it has to output here, output on the line, and so forth. And I can ask, instead of outputting epsilon, that you output points, and you can see that this is you are not allowed to output one processor from here, one processor from here, but you are allowed to output from here, and from here, as long as all the points that they output are from the same triangle, it's fine. And how will I solve it? I will take epsilon small enough, And sort of, if all the points will be close to this, I will take this. If you think of it, if I'll take an epsilon small enough, that has to do with Lebesgue coefficient, whatever of this. If I will take a small enough and will say to everybody, take the points closest to you, okay? Take the point which is, suppose that here, all of them are here. Then I'll say, you're close to a line. Take the point which is on the line closest to you, okay? And so I can have a rule that I can guarantee that they will return from the same point. But for this, I have to take this picture and put it in the plane and say this thing has a coordinate now. This node C has a coordinate in the plane, because when I'm doing epsilon agreement, I'm putting a point in the plane, and then I'm saying close and stuff like this. Okay? There should be also, what about, I'm not putting in the plane for you, I'm just telling you, if you go alone out from, and you don't see any other processor in another group, output A. And if you see from another processor, output on this line. And if you see others, output from here. And I don't do an embedding for you or anything like this. This problem is a problem without embedding. When we talk about task, we don't need to embed. A task has we can embed it, but there is no embedding. How do you solve the same problem? And this is a nice puzzle that you can give it in the class. I'll be surprised if on the fly some students can solve this. How do you solve this thing? Same thing with weights and stuff. Or it's not weight now. And without any embedding, there is no notion of where a node is in the plane. It's just given, and you know that it looks like this. Okay, so I will not go into algorithms now. It's a puzzle. Okay. So we move to the next thing, which is what is the 0, 1? What is the 0, 1 if we know that 0, 1 corresponds to if 0, 1 corresponds to election, and there is an algorithm in log n steps that will give us the election, what is the analog? We don't know. So we make an observation. And the observation relies on this previous epsilon agreement. Instead now of converging on a triangle, I'll try to even simpler problem, to converge on a line. Okay? So suppose we have a group here, and we have a group here, and I give them the task that they need to solve is actually two independent parallel consensuses. They need to solve consensus. Now, we know if the only thing we can solve is convergence on a line or convergence on a simplex, consensus is a very sharp thing. So if we could solve consensus, it will mean that we can, just between two values, what it will mean? It will mean do convergence, and if you finish on this side, output 1, if you are finished on this, output, and in between output 0 or 1. But if between output 0 and 1, I don't know where you'll end up with, and there will be a 0 very close to 1. I have to, essentially, if we try to solve consensus by epsilon agreement, from every point that you finish, you have to return 0 and 1. How do I guarantee if processes do not end up at the same point? How do I guarantee that they all will return the same value? What I will do, I will take the line, map it into all points into a 0 or 1. You cannot solve consensus. But what about if these two need to solve two consensuses independently? Okay? I can solve it. Why? Because I can do epsilon agreement. Okay? But epsilon agreement doesn't solve it. No, no, no. I will use the children puzzle that says kids want to impress. I can come to the other guy and say, I can win a chess against a master. No, you can't. How can you? I can. Let's bet. Okay, they bet. I will play 2 chess masters. And I will take the move of one, and one of them will play black, and the other will play white. And I'll take the moves of one and play to the other. I will play with 2 people the same game. Okay? And this Yuval knows, my mentor. This is one of the most important things, in my opinion, in distributed, and one of the most important things in cryptography. Also comes from a child puzzle, which is a child comes to the other child and says, I have a magic. I can look at a tree and tell you the number of leaves on the tree. No, you can't do that. No, no, I know. This is 2,000,005 whatever number of leaves. How do you prove him wrong? Turn around, take few leaves, now count again. You beat him on his own game. This is, in my opinion, this is zero knowledge. Okay. So what will be the game? The game here that in the 2, they will use the same exchange. They will do 1 epsilon agreement. They will not do epsilon agreement for the 2 consensuses. They will view this as a single line and will do epsilon agreement. So they will end somewhere. This line I'll take and I'll do epsilon. When I do epsilon agreement, there is always an epsilon. I will map these points in consensus 1, in this consensus, I'll map all these points into 0. I'll map all these points into 1. And there is an epsilon interval between that I will map to nothing. I don't know. Okay? You don't return from this. In this one, I will map this into 1. I will map this into 2. And in between, to I don't know. And what is the observation now? When you do epsilon agreement, you may fall into the I don't know area. But you cannot fall simultaneously in the 2 I don't know area in both consensuses because they are far apart. So, if I take 2 groups, and they need 2 groups, and they need to solve 2 consensuses among themselves, each one will return at least from one of the consensus. Okay? So, I may have another. What lets me say that I have 2 groups? 2-set consensus gives me 2 groups. Group 1, group 2. So I'll go the reverse. That 2-set consensus is a construct that everybody applies to 2 independent consensuses and get a value at least from 1. So K-set consensus is any number of processors that are involved. You get, to give the construct of K-set consensus to a number of processors is to give them a box with K independent consensuses. To each processor has a vector, what values it wants to apply of each of the consensuses. And when you return from consensus number 5, maybe you don't know who returned from consensus number 5 or who not. But all those that return from consensus number 5 return with the same value. Okay, so now I can have something that will be more analogous to a 0-1 consensus. Before we said, Soma said, the analog of 0-1 consensus is K plus 1 values to K. Now I say, no, it's K consensuses. And in the same way, you have 0-1 consensus in consensus, you now, each processor, the analog of 0-1 consensus, is each processor applies to the consensus with a value 0-1, and out comes a 0-1. Election is each processor applies his ID to all the consensuses and comes up with a value from some consensus, and this is the value that he returns. So we have still the analog of 0-1 and K election. Still the problem of how I give you K 0-1s. How from K 0-1s you do K election? I give you this now, I give you the K-independent thing that I give you can just take in 0 and 1, cannot take an ID, okay? What is the problem? Let's take 2. Let's take two independent consensuses. You apply 0 and 1, you return from process 2 with a 1. Now, you have to apply to the two consensuses again. We want to have the log, the analog of the log. You apply it to the two consensuses again. You may return from consensus number 1 before you return from consensus number 2. Now you return consensus number 1. But you don't know what was the value, the first value that was returned from consensus number 1. So how do you proceed? These two things that I showed you, for example, if I would like to do a 0-1, if I wanted to do a 0-1 consensus, and now let's say 3, how this thing will work with, I have 3 groups, and I want to solve 0-1 consensus. 3 independent 0-1 consensus. We know that 3 groups can solve Epsilon Agreement. Okay, 3 groups can solve Epsilon Agreement. So I will view, when they solve Epsilon Agreement, they essentially, I will view this line, projection of this line, as an agreement on one consensus, the projection on this line as an agreement on the other value, and the projection on this line as an agreement on another value, and you can convince yourself that I can arrange the area. You see, in each line there will be an area which, if you projection for them, you do not return. Okay? If your projection will for them, you do not return. And I can always arrange these areas so that there is no one point whose projection is on these three areas, 3 problematic areas. At most, you cannot prevent that there will be one point that will fall into problematic area. Another observation. Before we have seen these 2 groups, if they have 2 independent consensuses, they will return from 1. What about if the 2 groups have 3 independent consensuses? So I have 2 groups, and they work on 3 independent consensuses. Well, the generalization of the slides that I showed before will be, let's take 3 lines and say 0, 1, 0, 1, 0, 1. Okay? And now you can see that because these points, these areas, these problematic areas are far from each other, and I'm doing Epsilon Agreement, then I will return from 2 consensuses. Perhaps I have a generalization that says, okay, if processors can have choices, the number of choices is just k, if I have k vectors. But I have m independent consensuses. If you give me k independent consensus, I'll return from 1. For anybody extra, I will return from more. So I will return from m minus k plus 1. Okay? I will return from m minus k plus 1 because I have more independent consensuses, and the same choices. Here I have 2 groups. and two groups when I have two independent consensus return from one. Here I showed you, if they have three independent consensus, they'll return from two. If they have four, they will return from three, and so forth. This also applies to multi-valued consensus. Okay, here I will not go into the. These are you apply. Each one of them has a vector of. This is the vector, the red vector 1, 2, 3. This votes for. This is values. So one red is a value. One blue is a value, and so forth. Okay, so we now do multi-valued, not only 0, 1. I can solve multi-valued. I showed you that I can solve 0, 1. This is let's move on this because the details here. But this shows that you can, if you have three values and if you have three groups and you do a values, you can return from at least here. You can return from at least one value. And we have seen that if only two groups wake up and they have three choices, they have three independent consensuses, they can return from two values. So when you go on this border, you see number 2 here is the same color and number 3 is in the same color. So you move along this line, you preserve two values. And when you cross to the inside, you preserve one value. Okay, and of course, this picture that I showed you up to now was what I'll call a geometric algorithm. I took the lines and say in this area, if you fall in this area, but we can talk about distributed algorithm without embedding lines and stuff like this, just read and write and read and write and no interpretation of where in the space this thing sits. Well, there are algorithms for this and I will also skip it. Okay. So the question is, the main question that I want to get to is, how do you do, I give you independent consensuses that return 0 and 1. And from this, I want to do election. How do I do this? And I want to imitate the algorithm. In the first time we faced this problem, we solved it in an ad hoc manner, which the algorithm did not imitate the log n steps of the algorithm of consensus. What will be the analog of solving from binary consensuses, from k-binary consensuses, doing k-election? Well, remember from k-binary consensuses, you return only from one. You do not return from all of them. It's not just doing the same problem in parallel. And here, geometry helps us again. Before I said, this is what I called, when you want to solve consensus, there is a problematic area. That if you return from this problematic area, you do not know what to return. Say now, no. What about if there is some information here when you return? If this is the middle of the interval, and I'll take the interval to be of distance 2 epsilon, okay? Then when you return here, because the distance from any point here to any point here is more than epsilon, you know that if somebody returned, remember that, computer wants power too.